Hi, I'm Mateo Abegonzalez with ECTV. Today, we're talking to Ken Kilstrom, a retired professor of physics at Westmont College who currently works at the on-campus observatory.
Hi, I'm Lily with ECTV, and today I'm here with Ken Kilstrom. Thank you so much for being here.
Glad to be here.
So, can you tell us a little bit about yourself and what you do?
Okay, so I just recently retired from Westmont College as a physics prof. I had been there since the Reagan administration. I came fall of '84, and I've loved my time there. I did some research in superconductivity. I've also done a lot of the open viewings for the Westmont Observatory.
So, how did you start your career in physics?
So I've always loved science ever since I was a little kid. I actually remember telling my uncle, who was a chemical engineer, how lightning worked. And he dutifully nodded his head. And wow, really? You know, as if he doesn't know 5 times, 100 times more than I did as a little kid. But science has always fascinated me. I was given a telescope when I was 7 years old, and I couldn't wait for every evening to take it out. Of course, all I knew to look for was really the planets, the moon, and I would do that over and over again. But, you know, it got me fascinated. So I think all through, you know, my young life, I knew I wanted to do science. And then when I got to college, it was which science, you know, physics, chemistry, biology. And basically all of the professors, I talked to somebody in each department, and they all said, what are you good at? What do you enjoy? And in both cases, it was physics was my favorite. I kind of felt like biology was more useful than chemistry was more useful than physics, but they said, don't think of it that way. Part of it is the questions in physics, it takes more background to understand why you're asking them. You know, if you tell somebody you're in biology working to cure cancer, everybody nods their head. You know, if you say you're working on string theory, it's going to take, you know, a couple hours just to explain what that is, why anyone would care, why it matters. So I ended up in physics and have loved it.
What is your main career goal then so far?
Okay, so I really decided early on I loved teaching and I liked research. So I wanted to do both, but I liked the idea of having more of a focus on the teaching than the research. At a research university, all they care about is the research. They don't care if you can teach well or not. Whereas at a college, teaching is really critical, but they also want you to do research to involve students. And so, you know, really as a career, I love the idea of, you know, a liberal arts college like Westmont, and I've just loved being there.
So, you're a professor, obviously, you really enjoy teaching. What is something that you really like about it?
Well, I've sometimes said my motto is if I can't educate, at least entertain. And so I've laid on beds of nails, I walk on burning coals, I drink liquid nitrogen, mostly because if they think you might die, then they tend to pay really good attention. I once had this, one of my big demonstrations was to fill balloons, some with pure oxygen, some with pure hydrogen, some with a combination of both, and then light a match under each to see what would happen. Well, earlier in the demonstration, I have what's called a methanol cannon, where I have a plastic bottle with a cork on it and a couple of nails, and I send a spark, and I spray methanol inside, and then spark it, and it sends the cork at high velocity. And so that was going to happen first. And I set it off, and I know something's wrong, and I don't know what it is yet. And I'm just looking around, and my entire bag of hydrogen, oxygen balloons is gone. And the wall is filled with little bits of melted plastic. The flame from the methanol cannon ignited the hydrogen oxygen balloons and set them all off. And I look over at the professor who had brought this whole group over, and he's looking at me like I just strangled his cat. And then a kid in the front row goes, your carpet's on fire. And I look down and there's a flame and I'm stomping it out. So it's really fun to do things like that. It makes it very entertaining.
What might a typical day for somebody in your field look like?
Right. So, obviously a lot of the time during school year is teaching. At Westmont, we teach 3 classes. It could be a Monday, Wednesday, Friday, or a Tuesday, Thursday. And, it's hour 15 for the former, couple hours for the latter. And so that's a lot of your day. But you still do research during the school year, but you focus on it more entirely during the summer. And you involve students with that. And often there's paid summer research for the students, and they work alongside you, get the chance to actually do physics, be on published papers, that kind of thing as well. And there's committee meetings, and I love the faculty at Westmont. I love the students at Westmont, and just being able to talk with students. We would have students over at our house. Every Super Bowl, we'd have this massive Super Bowl party where I'd barbecue and it'd be a full meal and watch Super Bowl. So, it was a great environment.
In your time in the field of science, what are some interesting projects or some interesting research that you've taken part in?
So again, my fundamental research that I was doing was superconductivity. Those are materials that lose all resistance to electricity. And what does all resistance mean? So for instance, if you could have the purest copper wire, create a loop and get current flowing, and then remove your power source, it would die out in like 10 to the minus 8 seconds. With a superconductor, they've set up a loop of superconducting wire, started current going, and it's gone for years with no measurable decrease. And obviously, you can imagine practical applications of this. But my work was really trying to understand the fundamentals of it. What are the mechanisms that create superconductivity? How does it keep going? So I did years and years of doing that. It only happens at low temperatures. And for a long time, you needed liquid helium, which is more expensive per ounce than brandy, say. The holy grail was to get it above liquid nitrogen temperatures because that's less expensive than coffee. And eventually they were able to do it. But once they did, then how could you make this useful? And for instance, there was a company in town in Santa Barbara called Superconductor Technologies that made filters for wireless base station, like cellular towers. And the idea was to be able to block out unwanted signals and only let the signals through that came from the cell phones or from the tower outward. And we also worked with trying to do tunable filters, and we did some stuff with that. That was my fundamental primary research, was doing things like that.
You work at the Westmont Observatory. Have there been any interesting research projects conducted using the telescope there?
Right. So we've involved students there, and it's typically things like mapping asteroid orbits. It can be things like variable stars. So some stars get brighter, dimmer. And depending on the stars, they'll have different light curves, but we can measure the light curves of them. And so there have been things like that that our students have been able to get involved with, aside from just the amazing fun of just looking out into the sky and seeing things.
And you mentioned that the observatory does public viewings. What are some interesting things that you might be able to see if you attend one?
So things in the sky vary from time of year. So, when I got my telescope when I was 7 years old, and I loved taking it out every night. And, but what did I know to look at? It was the moon and it was the planets. I knew that if you looked at a star, even with the Mount Palomar telescope, it would just look like a star. So I didn't really know everything you could see. And there's this great story. A couple hundred years ago, there was an astronomer at the Paris Observatory named Charles Messier, and he was low man on the totem pole. And how you got to move up the totem pole was to discover comets. Comets were a huge thing. And how do you discover a comet? Well, you slowly sweep your telescope across the sky and look for a fuzzy patch. Now, is it a comet or is it just some piece of crap? Well, the way you tell is you mark the position carefully, and then you go back a couple nights later and see if it's moved. Comets move. Most fuzzy patches don't. And so you look and see if it moved. Well, he got so tired of finding these fuzzy patches and they didn't move, he started marking them all down. Well, by the time he'd finished, he had discovered 6 comets, for which he was now high man on the totem pole at the Paris Observatory. But he had made a list of 109 pieces of crap, let us say, that weren't comets that he didn't care about, and he's immortalized because of them. Because they're the 109 most interesting things to see in the solar system. It's the Andromeda Galaxy. It's the Great Nebula in Orion. It's the globular cluster in Hercules. And so if you have a kid that has a telescope, and what do I look at? Once he has seen the amazing things, the rings of Saturn are magical. The first time a kid sees the rings of Saturn with your own eyes, it's just unbelievable. The moons of Jupiter, phases of Venus, craters on the moon are all amazing things to see. But things like, the Orion Nebula are amazing too, and these clusters and nebula, it's Charles Messier has identified the most fun things to look at.
So within the fields that you are in, physics and astronomy, are there any theories that you believe within those fields?
So one of the things we say in science is every theory has to have the seeds of its own destruction. In other words, what experiment could happen that would provide evidence that would undermine your theory? Every theory has to be falsifiable. How would you tell it's wrong? And every theory is subject that some new evidence could come along. So hundreds of years ago, Newton, kind of figured out laws of gravity. And that withstood all the tests of time for hundreds of years until Einstein comes around and has to modify Newton a bit, that there are some things that it didn't explain. And so any theory, no matter how established, could be upended, at least to some extent, by further evidence. And so we always look for that. We always, hold things a little bit tentatively. And so sometimes belief isn't quite the right word as much as is the evidence supporting? So sometimes I think of it, would a physicist be willing to bet $1,000 against a loaf of bread that this ultimately is true? Because ultimately, nature, reality is what it is, and we're trying to understand it. It's not like, in some sense, philosophy, where you could always argue something is right, something's wrong, but is there any ultimate test to that? And it's hard to say that there is. But within science, nature is your ultimate test. An experiment is your determination. And as the ability to do better and better experiments happen, you have a better handle on, whether a theory is likely to be correct. Is it supported by the evidence? So in some sense, it's almost like a court of law. Is there overwhelming evidence, to convict, or is there reasonable doubt?
Are there any recent developments in physics or astronomy that people should be getting excited about?
Oh, yes. Yeah, I would say so. And one of the things that's great about the physics field and science in general, there's so many popularized books where scientists try to explain things that are going on in physics and in other fields to a lay person who doesn't have a significant science background. And so you have Stephen Hawking, A Brief History of Time. You'll have The Elegant Universe by Brian, what's his last name? Anyways, things like that kind of explain things like black holes and string theory and stuff. The things I'm probably most fascinated with, one of them is gravitational waves. So gravitational waves, we think of waves in general. You have water waves, sound waves, light waves. What are gravitational waves? That would be if there's some cataclysmic event that could create a gravitational wave. And it could be sort of a star collapsing into a black hole. It could be a collision of two objects, things like that. But how would you ever measure a gravitational wave? Because the whole idea of a gravitational wave is it's actually bending space. It could compress it in one direction, expand it in another direction, as it's saying, going through space. But if you had some, ruler to try and measure that, the trouble is that it would compress the ruler along with space, and you wouldn't be able to detect it. So what could you use that would be, light is really an absolute velocity. And so gravitational wave detectors make use of that. And they built two of these, one in Washington State, one in Louisiana. And the idea is you have these two long arms. They're like 4 kilometers long each. And the idea is send a beam of light, like a laser, that hits a half-silvered mirror. And so half of it goes down this way, half of it goes that way, and then bounces back. It's actually a little more complicated because it bounced several times. But the idea is when they recombine, if the peaks line up on peaks, then you'll get a maximum. If peaks line up on valleys, you'll get a minimum. In fact, it'll be a null measurement. And the idea is it can be very precisely null, when they can tune it so it is. But then the idea, say a gravitational wave comes through, expands one, contracts the other, then it'll throw it a little bit out of null, and you'll get a signal. So they set this up, and within 3 or 4 months, they get a signal. And it's a signal that shows up in both detectors, Washington State and Louisiana. And the idea of this is that the signals fall right on top of each other. And so they know it's real. It's not just somebody dropped a hammer on the floor and it vibrated things in one of the two installations. Well, then they analyze the signal and they're able to figure out what created it. And it came from something that happened 4 billion light years away, 4 billion years ago. And it was 2 black holes that collided. They spiraled into each other at half the speed of light, and in 20 milliseconds coalesced. And these were enormous in the sense of mass. One was 29 times the mass of the sun. The other was 36 times the mass of the sun. But when they collapsed, instead of a total of 65, 62 were left. So in 20 milliseconds, 3 solar masses were E equal mc squared into energy, into these gravitational waves. That means in those 20 milliseconds, more energy was put out by a factor of 50 than every star in the universe combined. Imagine that much power for that 20 milliseconds. But the other thing to think about is this happens 4 billion years ago when the Earth was mostly molten, a little bit of crust, and the Earth had to cool down, solidify, form a crust, form an atmosphere, have liquid water condense out of things, form life, go from, single cellular life to multicellular, develop through evolution until you have intelligent life that's intelligent enough to build a gravitational wave detector, in fact, 2 of them, and we made it by 3 months out of 4 billion years. That's pretty amazing. That's really a cool thing in recent science. And then later on, they detected 2 neutron stars. So a neutron star is where you have a star that collapses, and it's so much gravitational compression that the electrons are crushed into the nucleus and combine with protons to form neutrons. So it's basically a body made of almost entirely neutrons. 2 of these collided, and they were detected by the gravitational wave detector. But not only that, there were 6 different observatories that were able to actually spot it in another galaxy, and because it gave off a whole bunch of light at the same time. So, those are just 2 fascinating things that have been discovered.
So what advice would you give to somebody who is interested in going into this field?
Right. So there is a price of admission. Now, if you think about different fields, there are different entry requirements. If you want to be an engineer, for instance, you really need a bachelor's, but a bachelor's really is enough to be a good practicing engineer. If you want to go into architecture, you really kind of need a master's in architecture. if you're going to do physics, you really need a PhD. So it's not enough to just have a passion for science. You really need to be able to handle both the intuitive side of physics as well as the mathematical side. And that will be a barrier for some. But then also, it really does require a PhD where you really learn to do research under a professional researcher that shows you the way. And then you can go on and do research on your own. On the other hand, there's also areas of science where people know enough science that they can be a go-between between the professional scientist who does the work and the lay person who wants to understand it. And they could be the translator. So there's science education, that kind of thing as well, that you could get into. Plus, physics can be a great foundation to do other things. You know, physicists can often be pretty good in engineering, partly because it's almost like a Swiss Army knife. Every tool on a Swiss Army knife is inferior to the actual tool it replaces, but it does everything. And a physicist might do mechanical engineering 3/4 as well as a mechanical engineer, 3/4 as well electrical engineering as electrical engineer, but can do it all. And so there's some possible routes there.
And to finish off, do you think that your work has altered your perspective on reality or changed the way that you see the world?
My personal work, I don't know that I would say it has, but I would say in the realm of science, some of the things that have come out have just been amazing. There's a planetary system called the TRAPPIST system. It's 40 light years away, which, is a huge distance. You're not going to just build a rocket and go to the TRAPPIST system. 40 light years is an enormous distance, but it's a really tiny distance compared to, say, the width of the Milky Way galaxy. But what's interesting about it is that it's a dwarf star, so it's nowhere near as bright or powerful as our sun, and it has 7 planets circling it. The middle 3 are what's called in the zone of habitability, where you could have like liquid water. It might be favorable for life. I keep waiting for there to be a science fiction movie or book coming out about, Earth forming these giant space ships to go colonize the TRAPPIST galaxy or the TRAPPIST system. There's that. Because I think the biggest question that's really out there is there life on other planets? We can speculate, and there was some called the Drake equation that said, how many stars are there? How many of those have planets? How many of those planets are habitable? How many of those have water? How many could develop life and stuff? They figure there's got to be lots of life out there. But we don't really know if this was an incredible accident or if it's something that would happen commonly. So one of the biggest questions out there really is there life on other planets? And one of the interesting things is, a couple of decades ago, there was a meteorite found in Antarctica that came from the planet Mars that gave some indication that maybe there had been life on Mars. Now, how does that work? First of all, why Antarctica? Well, if a meteorite drops in the middle of Arkansas, it just looks like a rock. You may not pay any attention, not even realize it is a meteorite. If it falls in Antarctica, it's this black or brown rock in the middle of an ice sheet, and so it kind of stands out. Well, how did they know it was from Mars? Is it, made in Mars, except no substitute? Venus rocks are awful. How do they know? Well, it's because of trapped gases within the meteorite that match the Martian atmosphere. Okay, how did it get here from Mars? Well, the idea there is there would be some, giant asteroid or whatever hits the Martian surface, blasts it, sending up rocks, some of which, are able to escape Mars's gravitational field and start circling the inner solar system, and occasionally some find their way to Earth. So that's presumably how it made it to Earth. Okay, now why does it give evidence of possible life on Mars? Well, on Earth, there's this like bacteria type thing where it's got what's called magnetite spine, that basically its only sensation is it can sense the Earth's magnetic field. And In fact, if you go just north and just south of the Earth's magnetic equator, these things are aligned in opposite directions to follow the field lines, go up and down trying to find nutrients. Well, in these Martian meteorites, it looked like there might be fossilized remains of kind of chains that made you think, boy, that's similar to the type of primitive life we see on Earth. Maybe it means that there was life on Mars, because with Mars, it's believed that long ago it had liquid water, had oceans, and now it's dried up, and there's too thin an atmosphere to have liquid water. But it's an interesting question of is there life on Mars? Now, ultimately, what was decided of that, and the idea was, there's a saying in science: extraordinary claims require extraordinary evidence, and there's no more extraordinary claim than I found life on another planet. And so ultimately, they decided, while this was somewhat indicative, it's nowhere near conclusive proof. So they've kind of held off on that for now. That's kind of an issue. But and other things that you think of in terms of practical is, in Earth's history, we've had these mass extinction events. The most familiar to people is the death of the dinosaurs, that a giant asteroid hit the Earth. And basically, where the crater is mostly underwater, kind of off the Yucatan Peninsula, Gulf of Mexico, sort of thing. But the idea is it would have thrown up so much dirt and debris into the atmosphere, it would have blocked the sun for years, decades. And basically anything over 4 feet 6 on Earth went extinct. Nothing larger than that was able to survive it. But what caused that giant asteroid? Well, one thought could be, at the outer solar system, something called the Oort cloud, where there are basically comets, meteorites, all that stuff out there by the trillions. And what if a passing body, some rogue planet or whatever, escaped from some other star, kind of went through and gravitationally nudges those things, which were in stable orbits, but maybe it caused them to kind of plummet toward the inside of the solar system. Maybe that happens once every, many hundreds of millions of years. And maybe that's what's caused some of the mass extinctions, not just the one that killed the dinosaurs, but it's like the borderline between the Paleozoic and Mesozoic and Cenozoic tend to be marked by these mass extinctions where, often 80% of species on Earth went extinct. And that may be caused by the idea of some sort of cosmic impact with the Earth. I mean, we already believe the moon was broken away from the Earth by some giant impact, and that likely happened, earlier than life. But those sorts of things could be a little terrifying. We could all die, but the odds are very slim. Anyway, so.
Well, thank you so much for coming out and taking the time to talk to us. This was really interesting.
Yeah, and again, I would say, Westmont has open viewings on the observatory year-round, third Friday of every month. Now, it does help if the weather is nice. We cannot see through clouds. I once had the 5th and 6th grade school from a local elementary school. I set up an open viewing, and it was actually raining. I almost didn't show up. I should show up in case somebody does. And there were like 20 parents with their kids waiting in the rain outside the observatory. I'm going, we can't really see through these clouds. And they all go, oh my gosh, of course not. But that can be something that'll happen. And you'll get nights where it's partly cloudy and you're paying peekaboo through the clouds. But that's fun. And again, if you have kids that you give them a telescope, the moon, the planets are great to look at, and that'll keep them busy for a while. But the Messier objects are a great thing to look at as well for them.
Well, thank you so much. And I am Lily with ECTV, and thank you for watching.
And that's it. I'm Mateo Abba Gonzalez with ECTV, and thank you for watching.